Okay, I think that we can slowly start. I will just welcome and a lot of thanks to Professor Gia Dvali from Ludwig Maximal University of Munich to accept our invitation, and it's a great honor for us. And also I would like to thank and announce Professor Ioannis Rizos from University of Ioannina, who will be the host of today's session, together with Maria Dimitrievich from Belgrade and Mirela Babalik from Bucharest. We are the members of the program committee and try to make this program as interesting as possible. So Ioannis, please, the floor is yours.
Okay, thank you. So it's a pleasure to introduce Gia Dvali. I think he's a very well-known physicist, and he's professor at LMU and director in the Center of Cosmology and Particle Physics, and also director of the Max Planck Institute of Physics. I think he's very well known, so he doesn't really need an introduction. And we are very keen to hear his view on black holes, because he has always very interesting ideas and very exciting. So, Gia, please go on.
Well, thank you very much for the invitation. It's a great pleasure to give this talk. Yeah, so I will discuss some progress about understanding black holes. This is based on series of papers. Some of those papers are here together with my collaborators, and it views the black hole physics from very different angle, and the conclusions are pretty surprising and pretty eye-opening. So let me try to share this with you. Okay, so now black holes are considered to be one of the most mysterious objects in nature. Classically, they are eternal, they're stable, eternal. And they are a time evolution, and they are mysterious. They are considered to be mysterious because of their time evolution, and also the way they store and process information. So in particular, they evaporate thermally with approximately thermally. There is no exact thermality in nature. And with the temperature, which is given by the universe size. So they carry entropy, as we will see. Actually, that's a limiting entropy. But the surprising thing about this entropy, something that is considered to be very unusual, is that the entropy scales like area in units of Newton's constant. Okay, there is a factor of 4 here, which I'm not displaying these factors of force and pi's explicitly. They're not important for this discussion. So this is so-called Bekenstein-Hawking entropy, and so one question that is usually asked: why area and not something else? For example, why volume? Then there is another. These are all commonly accepted facts. I will only discuss things that are commonly accepted, are not really debated too much. So the other thing is that okay, you have this object that carries enormous amount of information because it has huge microstate entropy. So huge microstate degeneracy, and it emits energy. However, there's a minimal time scale that an observer needs to wait before of the start of the information recovery. Okay, so which is very strange. And this time scale is enormous. It's macroscopic, it's actually proportional to the entropy. Usually it's called pages time. And okay, it depends how you want to write it. It's entropy times the size of a black hole, or volume divided by Newton's constant. So it's a macroscopic time scale. Okay, so now the question that I was trying to, so basically what I'm trying to do for several years is to, so my idea is that black holes are beautiful, of course, and they are special, but they are, after all, they are not so mysterious. I mean, these properties that they have, these properties, they are not really coming from gravity. So basically, the question that I'm trying to ask now is, how special are black holes? Okay. And now, interestingly, this question was actually, I'm not aware of any type of posing this type of question in the literature. Not, at least not in the sense in which I will explain. And probably one reason is that this even to ask this question usually was probably considered to be ridiculous. I mean, why would you question that black holes are special? For example, if you have an object, let's say an apple, and a black hole of the same radius or the same mass, I mean, it's obvious that the black hole is very different. Okay, but this comparison is also meaningless. This statement is meaningless because in order to compare objects, we need to bring them to the same universality class. In other words, we have to compare objects according to certain parameters. And so this was actually never done. Okay, so the question, what is the universality class of a black hole? What are the types of objects that share black hole properties? So this is what I'm going to do first, as a first step. Now, the bottom line is that these mysterious properties of black holes, they turn out not to be related with gravity, but they are fully shared by a class of objects, a huge class of objects. And these objects are special in the following sense, that they have maximal entropy compatible with unitarity. So if you have a unitary theory, there is an object that can attain maximal entropy for certain given parameters. And so those are called saturons. And what is also very interesting, that the saturons exist in calculable theories, in calculable field theories, renormalizable, asymptotically free. And so the black holes essentially are saturons. So that's my point. So my point is that black holes are one representative of this huge class, and all the saturated objects, they share the same property. Now, in order to define this universality class, I will use Goldstone phenomena because it's very convenient, because it's trans-theoretic phenomena. It always happens. You don't need gravity for that, or you don't need something special for that. So as you know very well, I mean, whenever there is a breaking of spontaneous breaking of global symmetry, there are emergent gapless bosons, so-called Nambu-Goldstone bosons. For example, air in this room breaks spontaneously Poincare symmetry, and they are emergent Goldstone bosons. These are sound waves, and so on. And so this, based on this, I came up with this. So as a first step, so I came up with the following universal bound on entropy. Okay. So this is the maximal entropy. So if you have a unitary well-defined theory, and you have an object of certain size R, if you have a self-sustained object, the entropy of that object is bounded by the following expression. So the maximal entropy is area of the object in terms of Goldstone coupling. Now the area is something obviously that scales as the radius in power d-2. D is the number of space-time dimensions, and G gold is the Goldstone coupling. Now, in this bound, what enters are any Goldstone coupling, any symmetry that is spontaneously broken by the object. Okay. So the largest one is that gives you the bound. So the largest of these expressions is the one that gives you the bound. Now, as you know very well, I mean, the Goldstone coupling, we can trade, usually we trade for the so-called Goldstone decay constant. It's simply a square of it, inverse square. It doesn't matter whichever you want to use. This is just a notation. Now, also, we can define, so the Goldstone coupling, of course, is dimensionful, obviously. And its dimensionality depends number of space-time dimensions. But you can always define dimensionless quantum coupling. So dimensionless quantum coupling of the Goldstone. And here comes something very interesting. Again, I've never seen this being noticed in the literature. So then let me make the following observation, that if I'm interested in certain size sphere of certain size, and there's a characteristic de Broglie wavelength, de Broglie momentum associated with this sphere, with this wavelength. And so now if you are looking at the dimensionless Goldstone coupling, what dimensionless Goldstone coupling is the coupling similar to alpha electromagnetic, which sets the scattering of Goldstone amplitude, okay, the strength of Goldstone amplitude. Now that dimensionless coupling actually scales like area of a sphere of radius r. This is a very important observation. As we will see, this is the reason for area scaling of the entropy at the end of the day. So therefore, again, this is just a fact. It's just simply dimensionless coupling. This is not an assumption or anything like that. So in other words, we can use either dimensionful coupling divided by area or dimensionless coupling, okay, of the Goldstone. And so in this way, you can rewrite in two equivalent ways. The bound on entropy is it's either inverse of the dimensionless coupling, of course, evaluated for the on the scale r, momentum transfer 1 over r, or area divided by the Goldstone coupling. Okay, so now the question is, you can ask, where are the Goldstones coming from? Okay. Now the point is, and this is a very important point of my talk, is that any self-sustained object breaks Poincare symmetry spontaneously. Even if it doesn't break any other symmetry, it always breaks Poincare symmetry spontaneously. Therefore, there is always a Goldstone mode, which corresponds to the breaking of Poincare invariance by the object. The mode, I mean, a oscillator, quantum oscillator, with which is gapless, okay. Of course, in the limit large n, is gapless. And this Goldstone is well defined always. If you give me an arbitrary self-sustained object, unambiguously you can find what is the coupling of this Goldstone. You can unambiguously first construct this mode and then find its coupling. For example, if you have, so let's say a loose bound state of weakly interacting quanta of some typical wavelength r, let's say you have some sort of a wave packet, or a soliton, okay. You can easily calculate this. I mean, you can find this derivation in one of my papers, and so it goes like 1 over n, okay, times the area. This Goldstone coupling. Now, the states that you have high entropy, those that are saturons, that are in the same universality class as black holes, they also typically they contain other Goldstones. I will give examples. But the Poincare is universal. That's why it's very convenient to define bound in terms of this Poincare Goldstone boson. And so therefore, there are objects that saturate this bound, and they are called saturons. Now, it turns out that once I have such an object, okay, by definition, the entropy scales like area in units of Goldstone coupling, but there is also a minimal time scale of information retrieval, start of information retrieval. And this time scale scales like exactly like pages time. So it's proportional to the entropy times the size. Okay. Or volume times the decay constant of the Goldstone. Now, by now I have studied and with my collaborators and different combinations of collaborators and different papers. There is a long list of saturons in very different theories, ranging from gravitational type theories to even to QCD and renormalizable theories. They all have properties that are all these properties that we are considered mysterious properties of black holes. They are shared by these objects. They have, of course, area low entropy. They evaporate with approximate thermal way, with temperature given by the inverse size. Semi-classically, they have information horizon, and the time scale of information retrieval is identical to pages time, minimal time scale. They saturate scattering amplitudes. They exhibit the same bound on maximal spin as black holes. I'm not aware of any property, any mysterious property of a black hole that is not carried by these objects. Okay. So let me give you an example. It's always to discuss a particular example. I will give you two examples. Okay. Usually, in every talk I choose one or two examples. There are too many of them, and each of them is interesting because of different reasons. But okay, so here I decided, since this is maybe more sort of colloquium style stuff like this, there is an example which captures properties that could be interesting from many points of view, and they are also pretty generic. So here is a scalar field which transforms in certain representation of SUN group. Okay, I will call it a flavor group. I have chosen a joint representation, but it doesn't really matter. I mean, as long as there is some non-trivial representation, we can proceed. People are more familiar with the joint representation, and so yeah, I choose that. And so I will call it a flavor group, and depending from which community you are coming at, what are the problems that you are interested. This is a good prototype for many different systems. Okay, for example, if you are interested in many-body physics, you can think of this field phi as Gross-Kitaevsky field for a many-body object. If you are interested in solitons, you can think of it as soliton field, etc. If from Breckhoff point of view, you can think of this as some kind of metric field, etc. Okay, and we take Lagrangian, essentially most general renormalizable Lagrangian. Okay, now I want to take renormalizable theory. Why? Because I want to show that these properties, not only that they are not gravitational, they even exist in theories which are calculable and renormalizable, weakly interacting, very nice theories. So in order to remove this mystification of quantum gravity part. Now the only thing I'm doing here, so this is the most general renormalizable potential. I'm arranging it as a perfect square, so because it's easier to analyze. It's customary to arrange it as a perfect square, because then vacuum energy is at 0. But it's not necessary. So now, this field phi is an n by n matrix, Hermitian with 0 trace. So there are the following parameters. There is coupling alpha. Now notice I'm denoting this coupling alpha by the same coupling that I denoted this dimensionless coupling of Goldstones, because at the saturation point they are equal anyway, and I don't want to introduce new notations. And then there's a scale S, which will be a Goldstone decay constant at the saturation point. Okay, so we have this type of potential. Now, what are the characteristics of the theory? Okay, so here is something important. Now, this theory has fundamental coupling, which basically measures the strength of phi interaction. Actually, this coupling we can take arbitrarily weak, even to 0, because the dynamics, interesting dynamics, and unitarity in particular is controlled by what we call collective coupling and alpha times n. For those of you that are familiar with large MQCD with large number of colors, actually I will come back to that in my talk a little bit later. Sometimes we call this Stokes coupling. So then there's a unitarity bound. So unitarity bound, of course, is always within the degrees of freedom that you have. So you specify degrees of freedom in your theory, which are weakly interacting. These are phi's. As long as you are in domain of applicability where phi's are good degrees of freedom, there is a bound on the collective coupling. Collective coupling cannot be pushed farther than 1 or order 1. There's a critical value. There are many signals from there. Let me just discuss, bring one. For example, you can see immediately there are certain set of loop diagrams which are expansion in alpha n. Of course, the loops can be resummed, but that's precisely the point. When you push to criticality, the resummation is needed and theory changes the regime. So what happens, as we will see also later, is very interesting that if you try to go over that bound, and if you try to create an object which has more entropy, theory responds by changing the regime, and so, but you will never be able to make entropy larger than what I gave the bound. So this is also analysis is of course is simplifies in large and limit. In particular, we can take exact and going to infinity limit alpha going to 0 as long as we keep alpha n finite. Now this simple theory of what is theory? A joint or any other representation with most general renormalizable potential and weakly interacting arbitrary weak coupling. This theory contains saturons which share all the properties with black holes. Now to show this, let me show this. It's always good to see explicitly. You choose a vacuum. First, we choose the vacuum. Now this theory has many degenerate vacuum states. So there are different vacuum states in which the symmetry. So there is one with unbroken symmetry, SUN symmetric vacuum, and then there are vacuum in which symmetries are broken down to some maximal subgroups. I mean, it is sufficient to consider two only. So therefore, there is this vacuum, SUN symmetric, in which expectation value of phi is 0, and this vacuum has a mass gap. So in this vacuum, there's a mass gap, a minimal mass of particles. Then there is another vacuum, neighboring vacuum, in which symmetry is spontaneously broken down to a subgroup SUN minus 1 cross U1. So the phi has this form, and in this vacuum, there are gapless excitations in form of Goldstone modes. They are of order n Goldstone modes. Okay. Now you can also create a situation, since there are two degenerate vacuum. As I said, this is not necessary, but in this particular case, since there are two vacuum that are degenerate, you can create a situation when there is one vacuum, half of the universe, and the other vacuum in the other half, and they are separated by the domain wall. And for straight infinite domain wall, you can even find solution explicitly. The solution has this form. So you have SUN symmetric vacuum here, and SUN minus 1 cross U1 symmetric here. The wall thickness is given typically by the Compton wavelength of the quanta in the gap vacuum in the gapped vacuum. However, I'm not interested in straight infinite wall. What I'm interested in, I want to declare that my vacuum, our vacuum, is SUN invariant. So asymptotically, we are in SUN invariant space. And I'm interested in spectrum of objects in this SUN invariant vacuum. And this spectrum is very interesting because this spectrum contains bubbles of the neighboring vacuum. So there is a bubble. In the interior of the bubble, the symmetry is spontaneously broken. And in the exterior, no, it's not broken. And so you have an observer, asymptotic observer, Alice. Alice observing this bubble, vacuum bubble. And for Alice, this bubble is just like any other object. Of course, it transforms as a representation of SU, certain representation of SUN group, and so on. And okay, so this is the configuration for the modulus of phi. So it's inside the bubble is non-zero, and then there's a wall, bubble wall, and then outside it vanishes. Now the interesting thing about this bubble is that it's a highly degenerate state. In other words, because they're Goldstone modes, it has a large microstate degeneracy. So it's a very good candidate for a saturon because of gapless Goldstone excitations. And also, since we will deal with, so in other words, and correspondingly, this bubble can carry large amount of quantum information. And since the occupation numbers are large, we can always, it's also nice in large N, we also have a basic classical solution, just like for a black hole. You have classical solution, which is pretty good. And then you have quantum effects, which are also very important. And so now if, so that took now different possibilities. And so in the spectrum inside the bubble, you have Goldstone mode, so bubble has high degeneracy. Now, if you do not excite Goldstone modes in the interior of the bubble, then the bubble will start to oscillate. It will collapse and start to oscillate. The oscillating bubble is also can be a saturon and a very interesting object. But in this particular talk, I will focus on a stationary bubble, because bubble can be stabilized by the excitations of the Goldstone modes in the interior. Some sort of a non-topological soliton. Okay, you can create out of this bubble. So what you do, you rotate the bubble in the flavor space by certain frequency omega. Okay, and so in this case, the bubble is stabilized. Now, so there is a relation between the bubble radius, okay, it's given by the frequency. And so basically what you have whole spectrum of bubbles. You can think of these bubbles as bound states of Goldstones, okay, Goldstone modes, with the occupation number, which is given by this expression, okay. Now, so the energy of the bubble is given by the occupation number, is proportional to the occupation number of the Goldstone modes. And as I said, bubble is highly degenerate. It has a large degeneracy of microstates. And number of microstates in large N approximation, you can count easily and has this form. And you can derive corresponding microstate entropy. And the interesting thing is that this microstate entropy scales as n times a certain factor of logarithmic factor, which at the saturation point is order 1. Okay. So maybe this is the good time to show you. No, okay. Let me just first say this, and then I will show you the computer simulation part. Everything of all these can be this is derived analytically. You don't need numerical simulations for this, but numerical simulations are nice. So the point is this, right? So here again, now we have this bubble, and there is an asymptotic observer. Alice is observing this bubble, and this bubble classically is one object, but it has a huge microstate degeneracy, similarly to a black hole. And there is you can understand this microstate degeneracy in two equivalent ways. You can understand this as a degeneracy of Goldstone vacuum in the interior, Or you can simply understand the way that bubble transforms as an exponentially large representation of the flavor group. Both languages are equivalent. Okay. Now we can ask this question: which are the bubbles that saturate the bound that I gave you on entropy? In other words, now I'm interested in the bubbles which have maximal entropy that is given by the area in units of Goldstone coupling. Okay, so these are the bubbles that we're interested in. And see how their properties match properties of black holes. Okay, and so first of all, the saturation takes place for the bubbles for which all the scales are of the same order. So the size of the bubble is comparable to the Compton wavelength of particles. Frequency is also comparable. And so as I promised you that the Goldstone coupling was 1 over alpha. So it's given by this. So the entropy of this bubble scales like area in Goldstone units. Mass scales like entropy divided by R. These are both exactly the same scalings as for black holes. Now, the dictionary is that you have to remember that for black holes, Newton's constant is what is the Goldstone coupling of broken Poincare symmetry. Now, you cannot remember that because this was never discussed, this was never pointed out. So, but I am pointing this out. So if you analyze a black hole and you ask this question, what is the coupling of the Poincare Goldstone that appears because of the breaking of Poincare symmetry by a black hole? It's Newton's constant. So therefore, we should not be shocked why black hole has area low entropy, because that's how the maximal entropy goes. It's always area in units of Goldstone decay constant. And here is another example of this exactly the same scale. By the way, let me do the following thing. I have some sort of a couple of computer things just to make illustrative this point. Let me unshare and share this these pictures. So this is the. So you see the movie, right? Sorry, this is not the right. Yeah, okay. This is the, okay, let me show this. So this is the picture of a bubble that is stabilized because of the excitations of the Goldstones. Okay, so it doesn't collapse, it gets stabilized. But also what is very interesting is that this bubble has an information horizon. You see very clearly that up to 1 over n, the excitations, of the Goldstone excitations that carry information, they cannot propagate out, they cannot propagate anywhere. So the information is literally bubble acts like an information horizon, very similar to a black hole. Okay, now the same bubble yeah, the same bubble without Goldstone excitations, the bubble would dissipate. I mean, would collapse. Would collapse and then would oscillate and then finally would dissipate. Now, of course, as I said, at large n bubble is pretty strong, pretty long-lived. Of course, here for computer simulations n is not very large, and so yeah. Let me go back to the talk. Okay, so now. Now, next thing is that in quantum theory, this bubble decays by evaporating, actually, and strikingly similar to Hawking evaporation with temperature given by inverse size. Now, of course, what is nice thing here is that we are dealing, of course, this is a pure state. Obviously, we are in quantum field theory, unitary quantum field theory, weakly interacting, calculable. So it's a pure state, and you can trace how the spectrum emerges, how the approximate thermality emerges in the limit large n, in the limit infinite n, in double scaling limit, the semi-classical limit, thermality is very similar to black hole thermals. So, for example, here's a typical diagram how the Goldstone modes decay. This is a rescattering. The evaporation of the bubble is due to rescattering of Goldstone modes into an outgoing quanta. Okay, the nature of outgoing quanta doesn't matter. I just introduced some probe quantum in order to match Hawking's computation for black hole. What is important, of course, that the quantum carries is a representation of the flavor group, and so there are some typical diagrams of the enlarged and in Toast notations and so on. So it's very nice. Now, what is important is that so here's you have an observer, okay, and you have a pure state, and this pure state decays. Not any different from the decay of any other state, except the state is saturated. This is the key. And for saturated state, what happens is that the spectrum is strikingly similar to thermal. So of course, the spectrum at the end of the day, the state is pure. Pure state goes into pure state. But for Alice, in order to understand purity of the state, it takes a very long time. In other words, the purity of the state is hidden in 1/n corrections. So 1/n precision is required, and that takes time for understanding purity of the state. And of course, this is related with this is exact counterpart of what happens for black holes in semi-classical limit. In strict, the analog of semi-classical limit is this double scaling limit. When n goes to infinity, alpha goes to 0, alpha n fixed, and radius finite. And for infinite n, the saturon is eternal, just like a black hole is eternal for in semi-classical limit. But for finite n, none of the two are eternal, obviously. And information, of course, comes out over time scale, and that time scale is given by this formula. Okay, exactly like Page's time. So this is the time scale, the minimal time scale for us to start information retrieval, hidden in the flavor content of Goldstones. Okay, the black hole. So 1-to-1 correspondent with the black hole. So there is a black hole saturon correspondence. Correspondence in other words, again, I'm saying the formulas written in terms of Goldstone are universal. The mapping, this mapping is not really a mapping, because what I said is that the Newton's constant is a Goldstone coupling, simultaneously is coupling of Goldstone of broken Poincare invariance for a black hole, not for star, not for a planet, but for a black hole. And so therefore there is a full correspondence. Black hole is one particular saturon from huge class of objects. Interestingly, also in one of the papers with Florian Kühnel and Michael Zantedeschi, we noticed that the saturons they obey the bound on their spin, upper bound on their spin, identical to an upper bound on spin obeyed by black hole. Now, as you know, black holes they have maximal spin. Okay, we don't know why. I mean, we know why because if we demand absence of existence of non-singular solutions, but this is not understood microscopically. Why is this happening? And in saturons, we understand why this is happening, because what happens is that if you try to make saturon of very high spin, the saturon responds by vorticity, and and that doesn't allow you to have much higher spin, because vorticity just simply disrupts the solution. So so there are two things. First, we understand that the bound is strikingly similar, but also it's very tempting to postulate that bound on the spin on a black hole is probably of the same nature. Black hole presumably, not I'm sure, but okay, presumably represents high occupation condensate or high occupation state of gravitons, and then the assumption is that presumably for very high spin vorticity develops, and that is in conflict with increasing the angular momentum. The last part is an assumption; it's a conjecture. Very last part, right? Now, so let me. By the way, how much time do we have? I don't. You didn't tell me how much. How long should I? For how long should I speak, and then when to stop? But we started around 5:10. I assume, like, yeah.
Okay, like 6:10 or something. I mean.
Oh, 6:10. Okay.
Or 6:05. Okay, let's say.
Yeah, that's plenty. That's plenty. Thank you. Okay, so now I want to give. I want to discuss another aspect. So suppose you have a theory, and in this theory, you are creating a state, and then you are deforming your state or the parameters of your theory, so that the state becomes saturon. Now the question is, right, natural question. Why can't, what prevents me from pushing further? Now, as I told you, in all the examples that we know, and actually there, I also have very general arguments that pushing further is not possible, is because it's incompatible with the unitarity of the theory. So if you use the same degrees of freedom and make parameters such that the theory goes above this bound, the theory will change a regime. Okay, so we'll change a regime and prevent you from going over this bound. Okay, so let me give you an example, which is, I mean, extremely interesting. It also gives a new way at the confinement in QCD. So let me now discuss, therefore, saturation, phenomenon of saturation, and phenomenon in connection with confinement in QCD. Now, QCD, as you know very well, is a theory of strong interactions. It's one of the theories that, one of the most successful theories that we have, extremely well understood. And we know what happens in this theory, right? So this theory is asymptotically free at short distances, and therefore it's UV complete. It's a UV, so we don't need anything else at arbitrarily high energies for making the theory self-consistent. It's a self-consistent UV complete theory. At short distances, so this theory has a scale. This is a so-called QCD scale, QCD length. For ordinary QCD, this QCD length is approximately 10 to the minus 14 centimeters. Now, at short distances, this theory is a theory of quarks and gluons. Okay, so quarks and gluons are weakly interacting degrees of freedom. So they are good degrees of freedom. However, what happens is that at distances longer than QCD length, quarks and gluons become strongly interacting, and they are no longer good degrees of freedom. Not because they are strongly interacting, because they are simply other effects completely dominate. And so the good degrees of freedom at large distances are what we call composites. Glue balls, mesons, baryons, and so on. Okay, so the theory undergoes the change of the regime when we go from small distances to large distances. Sometimes this is represented in terms of QCD flux tubes. So we have, for example, you can put some probe colored sources, and these colored sources would have some sort of a would create some kind of color field. Not necessarily, of course, it's not precisely Coulomb field of a dipole, but some kind of color field. And so, but if you try to pull them apart at large distance, what happens is that the color gets confined in a tube. Okay. So the theory responds by creating colorless states. All right. Now there's a cousin of this theory, which we very often we like to consider this theory because it's simpler to analyze. which is QCD with large number of colors. Now, ordinary QCD has 3 colors. I'll come back to ordinary QCD, but we can make number of colors large. This is the approach which was pioneered by Toft and was shown, and we know that in this case, theory simplifies enormously. The analysis, certain aspects simplify enormously. So in other words, now what happens, right? So gluons. So this is gluon-gluon interaction in Toft notations. So each gluon is 2 arrows because gluon carries color and anti-color. So 2 opposite arrows. So let's say here is a gluon red anti-blue, and then anti-red green, and they interact, and then they produce pair of other gluons. Now at large N, this 1 color index of the produced pair is actually free. So therefore, gluon-gluons can produce some particular pair, but can also produce many others. And therefore, we have 2 types of couplings that we can distinguish. So one is fundamental coupling, which we call alpha QCD, which is coupling among particular gluons. And there is a coupling, collective coupling, or Toft coupling, which is multiplied by summation over n, and so it's alpha n. So this collective coupling lambda is so therefore in this theory we can actually take the limit, so it's planar limit, in which we can take n to infinity, alpha to 0, and keep lambda finite, and lambda is then the characteristic of the theory. So lambda runs, it's a running coupling. Okay, very good. So now lambda runs. So from if you are at short distances, lambda is weak, much less than 1. You can take lambda arbitrarily weak at short distances, and then you can run, and then at some point lambda becomes critical. Typically, this is something order 1 times some parameters which are not important. Okay, and where that happens, this theory beyond that confines, and so the scale. So in theory, you have dimensional transmutation. So there is certain scale beyond which the theory changes the regime. Okay, so this is what pretty well understood. This I'm not inventing anything new. However, now there is a new view on this topic, and my observation is that this point where lambda becomes critical and therefore theory confines, strikingly is correlated with the saturation of this bound on entropy that I gave at the beginning of the talk by a gluon state. There is a state of gluons of certain occupation number, and that gluon blob, or whatever you want to call it, or bubble, saturates that entropy bound simultaneously. So in other words, here's the point. So you have, imagine that we are, so mentally think about the following, about the following picture. Okay, now the QCD length beyond which QCD confines is a parameter of the theory. Okay, because this it just depends on the on lambda at short distances. So it's a parameter of theory, it's RG invariant. So for example, let's take a theory in which this confinement scale is like solar system or something, or even further. And so we are observers at short distances. At a short distance, we can create a bubble of gluons with occupation number. Okay, the occupation number given by typical occupation number, inverse coupling, but doesn't matter. Some occupation number, some characteristic size of these gluons. And then you ask the following question. Let me deform parameters of the theory. Let me make gluons longer wavelength. Let me add more colors to them. What happens when I do this? Gluon breaks spontaneously Poincare symmetry, the gluon bubble. Also, it breaks spontaneously the colors embedding in the color group. So the global color symmetry. And so it has entropy, microstate entropy. And the microstate entropy, you can ask this question: can I push it beyond the bound? And so for that, you can the expression is very nice. So this entropy is, I can write it as limiting entropy, this bound, plus log out of 't Hooft coupling, okay, for large 't Hooft coupling. So you see what happens is that in order for entropy of the gluon bubble exceed the bound, 't Hooft coupling has to become large. But that's not possible, because if 't Hooft coupling is large, then the theory changes the regime. So there is a correlation between confinement and the excessive entropy of gluon bubble, which is very, very interesting. So this looks like that QCD tries to prevent itself from violating the entropy bound. And therefore, beyond that, it confines, makes color unobservable. Of course, once color is not observable, there is no degeneracy anymore, because the colorless states, they don't have color. And so it produces colorless states beyond that point, okay? Now, so confinement is some sort of a self-defense mechanism built in in large QCD, or in general. I'll come to normal QCD, but in large QCD, certainly this looks like is the case. And it's a built-in mechanism preventing the colored gluon states from having the excessive entropy. So their entropy cannot exceed this maximal entropy area divided by the Goldstone coupling and so therefore beyond that they have to form colorless states and generate a mass gap. This is how theory prevents the violation of the bound. Now this is a very interesting parallel also from black holes, because what happens is that think about this gluon bubble as some kind of a ordinary object in gravity, right? Star, let's say. So you can try increasing the entropy of the star by putting more stuff in it or making it smaller, whatever. You can try to approach this bound. But what happens is that once you approach this bound, theory prevents you from going further, because first it forms a black hole, and then if you will try to increase the entropy of a black hole, it will just give you a bigger black hole. So you will never violate the bound. And in QCD, instead, theory confines and gives you blue balls and mesons and stuff like that. Now, what about ordinary QCD? Of course, this I was discussing large N QCD. In ordinary QCD, N is not that much, is 3. However, there is a candidate state in ordinary QCD, a very interesting candidate state, so-called color glass condensate. Okay, so this state has been noticed before, but was not noticed that this state shares the striking similarity with black hole high occupation number of state, and with saturation. And so Raju Vanugopalan and myself, we wrote paper last year arguing for that, and it's really striking. So this color glass condensate in ordinary QCD has all these properties that I just mentioned. Okay. Now, of course, in ordinary QCD, as I said already, I mean, 't Hooft coupling, since number of colors is 3. However, occupation number of gluons is 1 over alpha at certain scale. So occupation number of gluons is not small in the color glass condensate. But nevertheless, I mean, okay, so it's a very interesting view. And okay, what's the, so in large N, there is a clear-cut correlation between confinement and saturation of the entropy bound. And it looks like the color glass condensate in ordinary QCD is a candidate. Anyway, okay, so we have this, therefore, to conclude, we have correspondence between ordinary theories, saturons in ordinary theories in gravity. It's 1-to-1, and it's based on trans-theoretic parameter. That's why I chose Goldstone coupling and Goldstone coupling, either dimensionless or dimensionful, doesn't matter. And so we observe a complete correspondence. So yeah, there are other examples yeah, one I already mentioned, Calgraph's condensate. I don't know why I'm repeating it here, but even in two-dimensional calculable models, like Gross-Nivier, for instance, which are again asymptotically free, fully calculable, they are saturons which exhibit literally same properties of black holes. We've shown this, Otari Sakhalashvili and myself recently. Okay, so therefore, just to move towards the conclusion is that it looks like that the mysterious properties of black holes, I mean, that's a fact. So now you see, I tried to present facts. Then, okay, there's a question of interpretation. So what we are observing is that these mysterious properties of black holes, they are not rooted, looks like they are not rooted in gravity, but are shared by this large class of saturated states, saturons. And there are many examples. And as far as we can see, they all share all the features of black holes. Now what can we learn from saturation? Now we see that since saturons appear in calculable theories, now we can observe certain properties that normally would be blurred by quantum gravity or whatever computations in quantum gravity. Here we see it very clearly. And now we can learn from these saturated states, and now we can expect similar properties in black holes. There are two important properties. One is that evaporation is never thermal. It's always corrected by 1/s. This is very important. And also, the standard assumption about black hole evaporation is that it's self-similar. That when black hole evaporates, becomes a smaller black hole, essentially indistinguishable from a smaller black hole. By the way, that has never been justified by any computation, because that requires semi-classical computation by taking into account back reaction, and that nobody has done it. Hawking computation is done in the limit of 0 back reaction. So without essentially any evidence, we always have been assuming that the black hole evaporation is self-similar. What saturons tell us that this assumption, there is absolutely no evidence that this assumption is necessary. So it could very well be that when black holes, and most likely that's the case, that when black holes evaporate, the remaining state is not identical to a smaller black hole, but it's very different. In other words, black holes age. There is a quantum clock because of evaporation. They age, and so the evaporation is not self-similar. And beyond half decay time, we cannot extrapolate semi-classical computation. We have to redo computation and see what happens after. And some interpretations also. Now, since in all the examples of saturons that we know, saturons are either solitons or other bound states. So they're solitons or gluon bubbles or instantons or baryons and so on, or Gross-Nivier bound states. In all those examples, of course, saturons are high occupation number states, critical states, saturated states of high occupation number of quanta. Now, this, of course, this indicates that black holes probably are the same. Also, they are saturated high occupation number states of gravitons. Now, this idea is not new, but I deliberately didn't mention it because actually what I wanted to do, I wanted to distance myself from offering any microscopic theory of a black hole. But this idea was proposed by Cesar Gomez and myself a long time ago. So we have a theory, microscopic theory of a black hole, in which black hole is described as what you can now call a saturated state of high occupation number saturated state of gravitons. And so what we observe recently in other saturons, and this correspondence very nicely supports that idea. Okay, I have to finish here. It's 6:04. So there are such saturated states also in non-relativistic many-body systems. For instance, here is one example of a simple bosonic system, in which you have a sort of a critical state near which we can have saturated state, and so on. And so these are the sort of rainbow of microstates near the saturated state in this non-relativistic system. So I'm bringing this why, because saturation doesn't have to limit itself by relativistic states, not by relativistic systems. Okay. Yeah, there are many other implications. Of course, unfortunately, in one talk we cannot discuss everything, but there are other implications of saturation, very important implications actually in cosmology. For example, for the de Sitter state, de Sitter also there is a very strong evidence that de Sitter is a saturated state, and that's why, by the way, de Sitter is excluded as a vacuum in quantum gravity. That matches very nicely this other claim of ours that in S matrix, because of S matrix formulation in quantum gravity, we cannot have de Sitter, eternal de Sitter state, and so on. Okay, thank you very much. And of course, if there are any questions, I'll be happy to answer.
Thank you very much, Gia, for the very interesting talk.
Thank you.
Are there any questions? These are about 40 participants, so I can't see everybody. So if somebody wants to ask a question, please go on.
Can I have a question?
Yes, please.
Yes, of course.
Hello, Gia.
Oh, hi.
Nice
How are
talk.
you?
Thank you much. Gia, I was wondering, can you explain a little bit how you identify Newton's constant with the Goldstone constant for black holes? Is it related to event horizon or any other property? I mean,
Yeah, it is very simple. So let me see. Maybe I even have a transparency somewhere. If not, I will explain. No, I don't have transparency, but I can explain right away. Let me say something. Let me take some picture.
Because you say that it is not valid for stars, for example.
Yeah, absolutely. So that's very important. I hoped I had a picture, but okay, if I don't have a picture, maybe I'll just explain it with words. Yeah, here's the point. Okay. Now let's imagine that we have a star, right?
Right.
Okay, so now the star breaks Poincare invariance also spontaneously. Now the star has constituency because of ordinary particles, and it has constituency because it gravitates.
Right.
So in other words, star breaks spontaneously Poincare invariance because it's a star, and also because it has a gravitational field, which gravitational field of this star is also not Poincare invariant.
Okay.
Now, if I'm an asymptotic observer and I identify deviation, so the order parameter from the point of gravity, the order parameter of breaking Poincare invariance is a deviation from the flat metric, from Minkowski metric.
Yes.
Okay, so very good. Now,
because it is the curved geometry itself, that means okay.
Yeah, but it's literally the order parameter is the gravitational field, which is a deviation from the flat metric, because flat metric doesn't break Poincare invariance.
Thank
so
you.
the metric perturbation that is not flat, whatever else, that is the one that is breaking Poincare invariance. Now that metric perturbation reaches. So if I have an ordinary star, at the surface of the star, that perturbation reaches something that is much less than 1.
Right.
Okay. For example, if we near the surface of the Earth, because Earth is approximately, what is the radius of the Earth? It's 10 to the 8. Earth is like 10 to 8 centimeters, right? Something like that.
Yes.
So the Earth is much larger than its own gravitational radius. So therefore, that metric perturbation reaches maximum at the surface of the Earth, and that is approximately 10 to the minus 8. Okay.
Yes.
Now, Now we have to translate that perturbation in terms of canonically normalized graviton, okay?
Good.
And that is Planck mass times 10 to the minus 8. So in other words, the counting is very simple. The order parameter, which is represented by canonically normalized graviton, at this reaches its maximum, which is m Planck, and then times a small number, which is the ratio of the actual size to the gravitational radius. Sorry, the other way around, gravitational radius to the actual size. So that's why the order parameter for breaking Poincare invariance is much less for any other object by gravitational field, is much less than the Planck mass. So the maximum is given by black hole, because for the black hole, the order parameter reaches Planck mass. The canonically normalized graviton reaches Planck mass at the horizon. So that's why this F, scale F, for a black hole is actually the Planck scale, okay?
Okay.
So that's why the Goldstone decay constant is 1 divided by Planck scale square, which is nothing but Newton's constant.
Great, great.
Now,
great.
in our picture of black hole, a composite picture of a black hole, that you can also understand very nicely. So the composite picture of a black hole is a bubble of large number of gravitons of occupation number n, which is actually given by the entropy. So 1 over the black hole entropy times the radius. And then again, you can check explicitly that this is precisely Newton's constant. So again, yeah. So, but yeah, this is a very important question. Yes, thanks for asking.
Thank you very much for explanation.
Okay,
Very
there is
good.
another
Thank you.
question. Professor Mashoud, please go on.
Please.
Yes, yeah. So, Giora, this, as I understand, this saturons has no relation with dark matter, right? Dark matter is absolutely aside of this, right?
No, it could be dark matter. I mean, saturons could be dark matter because, for example, a trivial example is, for instance, because we know that since my point is that black holes are also saturons, and primordial black holes, they can be dark matter, actually very nicely. They can be dark matter. So therefore, yeah, so saturons certainly can be dark matter. Now, more interesting from that point of view are saturons which are not black holes, because non-gravitational saturons in a certain sense are even more interesting because nobody was considered them before. And yes, they certainly can be dark matter. And actually, they are very interesting dark matter. With, in various models, they appear because they have very similar properties. They are extremely long-lived.
Yes.
Yeah, they're extremely long-lived, and they have very interesting signatures when they evaporate, since they evaporate like black holes, but in a very specific spectrum. And so, absolutely, yes, saturons are very good candidates.
But the point is quantitatively, is it really enough to have this so much?
Yeah, so now,
or you need some other things in addition, like, for example, actions and such things.
Yes, let me add this. Actually, that's a good point, because precisely, as you know, in ordinary black hole dark matter, in ordinary primordial black holes as dark matter, there is an issue of their formation.
Yes.
And because since they are gravitational, there are not many formation mechanisms that are successful and do not require fine tuning, etc., etc. Although there are many proposals, most of those proposals they require either fine tuning or some coincidence, because of the obvious reason, because to produce a black hole during inflation, for example, you need large perturbations, and you need perturbations that are just right, not large enough to produce black holes, but to be not to overclose the universe and so on. And I mean, there are some mechanisms. We had some proposals recently also to produce black holes from confinement, etc., etc. But anyway, there it's a challenge. So it's a general challenge. In non-gravitational saturons, the production mechanisms are much simpler because they are not directly tied to inflationary epoch. They can be produced during thermal phase transitions and so on. So with my experience playing around, of course, that's model dependent, obviously, but with my experience playing around, non-gravitational saturons are easier to be encountered for dark matter than black holes. So yeah. So yes, thanks. That's
Yes, another question is that there is no way that there is a CP violation here, no?
No, CP violation could be on top of it, of course. That's not excluded. I mean, you don't require necessarily that saturons be CP. I mean,
yes.
Yeah. So in other words, there is no, in order to saturate the entropy bound, there is no a priori requirement about CP violation. But there can be objects which are CP violating objects. For instance, one of the things that makes, as you know very well, one of the things that makes theta angle in QCD observable are instantons. And actually, instantons, they also can be saturated objects in large QCD. In fact, there is an interesting correlation that it's a similar correlation. So in large QCD, instantons become saturated at the same scale at which confinement sets in. So there is also this correlation. So from that point of view, there can be indirectly connection. Yes, thank you.
Yes.
Okay, I see another question. Thank you. But I can't see the person who is asking. Please go on. I see a number, 382,526.
Thank you. Can you hear me, please?
Yes, sure.
My name is Miroljub Dugic of the University of Kragujevac. As a quantum physicist, I would like to ask a few questions, if I may, for my own purposes. I'm not familiar with this stuff, so I hope my questions won't be unreasonable. My first question is that, as much as I recall from the start of your talk, by the way, thank you very much, which was very inspiring for me. You mentioned something like self-sustained systems.
Mm-hmm. Right.
What is the meaning? Does that mean that the self-sustained system is isolated? Actually, nothing outside.
Yeah, I mean, it's okay. Of course, as usual, I mean, there are no truly isolated systems in nature. It's very hard to produce anything truly isolated. But self-sustained means that it should be isolated within a good approximation. So in other words, we can make it more quantitative. So what is required, that the influence from the other sources on this system on the timescales of interest are small. So then all these considerations, of course, go through.
May I link that to the assumption of unitarity?
No, that's on top of unitarity, because it's like, let's think about black holes, right? So let's say we have black hole at the center of the galaxy. When we say that this black hole carries entropy, et cetera, of course, we ignore accretion, for instance, because obviously accretion and external effects, they constantly change parameters of a black hole. They change mass of a black hole, they change the radius, and so on. So of course, when we talk about a well-defined entropy of a black hole, we assume that we ignore the processes, accretion processes, which of course change those parameters. So it's the same thing. It's just simply you have to have a system which is sufficiently well isolated with the margin, with the error that is good for your counting. So for example, if in laboratory, for instance, I gave you this example. For instance, this is, for quantum laboratory. Let me show you again. Sorry, I went too far from here. So for example, here, right? This is a system that this is the simplest, in certain sense, it's the simplest system that you can imagine. These are bosons in a box, one-dimensional box. So it's 1 + 1 dimensional system, non-relativistic. These are bosons with attractive delta function type interaction. So the simplest interaction you can imagine. So it turns out that already in this system, there is a potential for producing saturated states. Why? Because saturated states, they require 2 ingredients. They should have entropy, high entropy. This requires gapless excitations, appearance of gapless excitations. And then you need diversity of those gapless excitations. So here, for example, you see explicitly that when you approach certain critical state, a frequency of, there is a mode that emerges with very low frequency, okay?
Okay.
Now, of course, as usual, I mean, obviously, this frequency is subject to error because since here n is not that large, these are computer simulations. So n is of order 100 or 10 or so on. So correspondingly, the frequency is also subject to an error. But nevertheless, as you can see, despite the fact the frequency is dramatically lower than a typical frequency in this system. So yeah, so that's the question. You minimize the error, and depends what you want to do with the saturated system. For example, if you want to, I don't know, produce some entangled state, etc., correspondingly, you have to lower the influence from the external sources. Yeah.
Another, if I may, related question to me, which something confused me as a quantum physicist, I have to repeat, is that you mentioned the spontaneously. What is the meaning of spontaneously? Typically, the decay of the bound states in quantum mechanics are only and exclusively due to influence of the environment. For instance, no atom can be regarded a closed, an isolated system, or even a closed system. It is non-unitary. The internal degrees of freedom of the atom are monitored by the quantum vacuum fluctuations, as it is.
Yeah, so you presumably, indeed, I mean, you presumably meant when I mentioned spontaneous breaking of symmetry.
Yes, indeed.
Yeah, so the spontaneous breaking of symmetry is a term which has nothing to do with really something happening in real time. So spontaneous breaking of symmetry means that you have a system. In certain sense, it's an unfortunate term but historically that's how that's how it came. So we say that a given system breaks certain symmetry spontaneously when the Hamiltonian is invariant under some symmetry, but the ground state is not. For example, a typical example, right?
I understand.
Yeah, typical example that people bring is, for example, ferromagnet. When you have ground
just
state.
in a quantum phase transition.
Right. So of course, this doesn't mean when we say that system breaks symmetry spontaneously, this doesn't mean necessarily that we are referring
dynamical
to
process.
Yeah, we don't really refer to some process that is happening in time. It's just a property of the ground state. So yeah.
Okay. And my last question would be, what kind of change of the degrees of freedom when, as you told, as I have actually understood you, your theory breaks or is not actually, it changes? Which kind of change of degrees of freedom are assumed? Are those, for instance, linear or something more complicated?
So it's so you are familiar with Bogoliubov transformation, right?
Sorry, I didn't hear you. I'm familiar with.
So Bogoliubov transformation.
Yes, indeed.
Right.
Sure.
So for example, think about some kind of condensate. For example, here, right? So this picture is actually a good reference point for that. Now, what happens is that if I have a condensate which is interacting, so depending on the parameters of the state, for example, depending on the occupation number and the strength of the interaction, which usually translates, a good parameter for that is this collective coupling. So what happens is that when collective coupling is weak, so you have one ground state in the system, and degrees of freedom are, let's say, ordinary particle excitations. Okay?
Okay.
Now, what happens is that these ordinary particle excitations, they stop to be good degrees of freedom when you pass this critical point, beyond which the collective coupling becomes, if collective coupling becomes order 1, what you have to do Bogoliubov transformation, a canonical transformation.
Which are linear, okay.
Which, typically is linear, but of course it's not guaranteed. For example, it could be even much more complicated transformation. Yes, in this particular example, absolutely. The linear transformations are fine.
Okay.
Indeed, but in general, the transformation may be pretty involved.
In general, not necessarily.
Yeah, exactly. So it would be.
Thank you very much.
Therefore, degrees of freedom change, and so, for instance, in this example, degrees of freedom become some sort of solitonic degrees of freedom are the ones that are now good degrees of freedom, and so on.
Thank you very much.
Actually,
thank you very much.
This picture explains it. So this is one type, then and then the second regime.
Are there any questions?
Thank you very much.
Thank you.
Okay, I think are there any more questions? We have to thank Gia again for the very interesting talk, and
Thank you.
we have to give some time to think in these new ideas presented here, all of us. So thank you very much once more, and see
Yes,
you
thank you very much for the
at the next
invitation. Thank
seminar in about 1 month from now.
you. Okay,
Okay,
bye.
bye.
Thank you.
Thank you.
Bye.